So now this is how you do computations, but you have to also store the results of your computation. What is the most basic element that stores a value using logic, using silicon? Not a flop. A flop is like a half of a flip. No. The basic element is called the latch. And this is a latch. This is from Wikipedia. A latch has two legs, set and reset. If you go to Wikipedia, you will see it animated. It's not animated here, too bad. If you set S to 1, then the output becomes 1. And then if you move it back to 0, it stays 1, which is awesome. If you set reset to 1, the output becomes 0. And if you move reset back to 0, it stays 0. If you set S and reset at the same time to 1, then you get undefined behavior. You don't get a fire, at least you don't get nothing burns down, but you get an undefined behavior. So you don't want that to happen. So Latch is the basic equipment, but you can build a more interesting device. It's called a flip-flop, as Oya is very formal, referring to flip-flop only in the last name. Flip-flop in Hebrew is Zaglag, and here is a bunch of flip-flops. So how does the flip-flop work? It has an input called this is a D flip-flop, it's the basic one. It has an input called D, and every time there's a rising edge on the clock goes from 0 to 1. What is in D is copied and it's going to be now in Q. And it's very, very useful to do logic devices this way, because what you do is you have a clock which is shared between all the devices in the system. This is 5 MHz, 2 megahertz, 3 gigahertz, and so on. And every once in a while, you bang this big gong, and all of the data goes out to the next step. And of course, between D and Q, between this step and the next step, it doesn't have to be a direct connection. You can have sorts of logic devices and logical elements which do all sorts of computations. But you wait enough time between the clocks so that all the computations are finished. So you bang the drum, there's a big shift because all the D goes to the Q, and then they run around and do all the logic, and then you do bang the drum again, and this is how you do synchronous logic. It's very useful. And you can think as an attacker, if you bang the drum too quickly, what happens? Then you have what is called a hold time violation. It means that some of the devices, some of the flip-flops haven't finished calculating it, and then you have sorts of crazy stuff going on. We'll talk about this when you fall to next. Synchronous circuits are very helpful for the attacker. And why is that? Why is that? Because all of the flip-flops switch at the same time. This is a very powerful signal. So an attacker is it's very easy or easier for an attacker to detect this bang, this change that happens on the clock, because everything is synchronized. It's happening at the same time, and where the logic is scattered all around. Fine. So if you take a lot of these devices, sequential circuits and logic circuits, and you combine them together on silicon, you get what is called an integrated circuit. So here is a basic integrated circuit. This is what is this? What is this? This is a Core i7 CPU, and this is a picture of it. And you see there are many transistors in here, and you can see, even if you inspect it visually, that they look kind of you have all sorts of areas. There's lots of differences between the two. It's not a Pentium; it's a Core i7. A little newer. So let's see what we see here. So you see that there are areas which look different than the other areas. So there are areas which look very uniform. You see these arrays, they're very patterned. And there are things which are kind of crazy and look like spaghetti, right? So the areas which are uniform are usually the storage, because there's like an array of bits you need to store. And the crazy stuff is usually logic. So if you also look closely, you can see that there is some copy pasting going on in this device. So you see there are 4 things here, which are also here and here and here. There are 24 of these things Does anybody know what these are? 24. 24 what? What are these? Anybody know? No, they're not 24 registers, not 24 caches. So this Intel has an onboard integrated GPU with 24 execution units. So each one of these is an execution unit in the GPU. Now, do you see that there are 4 things here which are very similar? These big fellows, this one, and this one, and this one, and this one. What are these? Yes, correct. These are the 4. This is a quad-core processor. You see that inside the core, there are these small memories. These are the caches, right? So now I can just show you the legend, and this is what Intel is saying. So there is the GPU here, and it has the computer has all sorts of calculations. Also, it's doing MPEG decoding and DRM and all that. And there are the cores, and this is the cache which is shared between them. And this is all sorts of integration with HDMI controllers, USB controllers, DisplayPort controllers, and so on. Lovely. So very cool. Now, what am I interested in as an attacker? What's interesting for me as an attacker is that the power consumption is variable. It's a function of what's going on inside the device. And I want to show you a very basic measurement circuit which measures. So what you see here is the NOT gate from before. And there is a difference between the NOT gate that I showed you previously and this one. What is added here? Can anybody tell me what changed between the previous time I showed you this one and this? There is something new. Yeah, they're the capacitors, right? There is C1 and C2. C1 and C2 are capacitors. And actually, these are these capacitors. I didn't want to add them. Actually, I'm not very happy about the fact that they exist, but they are a function of the fact that there are cables. There are cables running here inside the device, and this is what there's a charge and discharge. Somebody mentioned here. You can imagine this is the ice cafe, which is inside the straw, if you want to use a metaphor. So when I change between 0 and 1. I put current inside, and this is what I measure. Now, if you look below here, you see there is my ampermeter. So I cut the power supply, and I put my ampermeter. And now I'm going to connect this to an oscilloscope. And sadly, I don't have an oscilloscope to show you because I'm in quarantine. But an oscilloscope is a device. It's like a baby monitor. It measures the x-axis is time, and the y-axis is the power consumption. Let's see if it's in. So what you see here, so the x-axis is time, and you see this is the output. So the output goes between 0 and 1 and 0 and 1 repeatedly. And if you see here, most of the time, there is virtually no power consumption. And this is because the device is stable. So one of these networks is active, the other one is open, so there is no current going between the input and the output. But every time there is a transition, I get a peak, I get a little pulse of power. So there is a high power consumption when I go between 0 and 1, and another high power consumption when I go between 1 and 0. Why is there a difference between the two values? Why is there a difference? Does anyone have any idea? So this is the effect of the capacitors. So when I'm moving from 0 to 1, I am, metaphorically putting the ice cafe inside the straw. So I'm actually I'm working harder. And when I'm moving from 1 to 0, I am essentially, getting power for free, which is stored inside this charge and discharge. So so this is a very detailed model of the device, and I'm going to show you after the break that you don't have to be so intricately involved in the design of the circuit to do what is called power analysis. So let's have a